Okay, so GCM modeling. I said transport and radiative effects, but it's a lot more than that, of course, because GCMs are like that. I'm Laurie Neary. I work here at BIRA as well. And this is also, again, combined efforts of people on the Nomad team, and especially my partner in crime, Frank Darden, who's hopefully online. We're the GCM modelers here at the Institute for Mars, I should say, because there are other modelers here. So just to give you an overview, I'm going to introduce a bit about GCMs and what it takes to make a GCM. Review a little bit the characteristics of dust in the Martian atmosphere from the perspective of how do we model it. What we do in models right now, what we would like to do in models or what we don't get right in models, things, open questions that we haven't solved yet, and then maybe some useful resources. Modelers love pretty animations. This is not mine. It's from the UK Met Office model, but it's a good one, so I put it in there. So first part, modeling. First of all, I know we've all discussed this in this workshop mode, but what is it good for? Why do we do modeling? You've all seen those gaps. Lucas showed it perfectly, the gaps in the observations, what happens when we're not looking. We can use models for that. We can use it to understand these processes that we may see something in the atmosphere. If we can model it and get it right, does that mean we really understand the process, or do we get the right answer for the wrong reason, or things like that? So it really helps us to figure out what we're missing. Sometimes it's just difficult to numerically represent a subgrid scale tiny thing that happens in the atmosphere, but we're always trying to figure out ways to do that. You can use models for past climate, of course, studying the evolution of planetary atmospheres. And then in the other direction, we can use modeling for forecasting. And we've heard about data assimilation already, and using the model combined with observations to not just forecast, but also to, again, enhance our understanding of processes and how we represent them in the model, and what we see in the atmosphere versus how we numerically represent it. And of course, you saw from Loic and others, we use the GCM for inputs into the data retrieval process, so an input atmosphere a priori. So keep my job, please. It's really important. Just an overview of the different kinds of atmospheric models. You can have just a single box and integrate that forward in time and see how it behaves. You can stack a bunch of boxes on top of each other and call it a column model, and that gives you also some very interesting information. You could then take that column model and put them all together on a sphere and have a 3D GCM, which is mostly what I'm going to talk about today. Actually, it's all I'm going to talk about today. But you can also, very interesting for Mars is to do regional scale or mesoscale. They have different names for this higher resolution modeling. So this is on the order of typically hundreds of kilometers. When you want to represent the whole globe, modelers are super impatient and they want the answers now. So computationally, we tend to keep our grid boxes on the order of 100 kilometers. But if you want to look at things, so now we have all these landers and stuff, and they land in these craters. A GCM does not really resolve the crater walls or anything like that. It's just kind of a field. So you can use regional scale or mesoscale models on the order of tens of kilometers to look at processes that are like slopes, winds on slopes and things like that. And one of the reasons sometimes, so you can run mesoscale tens of kilometers on the whole globe if you're very patient, but often we just use a subset of the grid. And if you can imagine this crater here, the wind is going to blow across it, so you need to provide boundary conditions so you have a larger scale model in the background. Sometimes you have to nest quite a few times, so it's also computationally expensive. But once you do this run, then you can do short-term, you can do testing and things like that. So regional scale, mesoscale models are also really interesting for Mars. On the order of meters, you can do large eddy simulations. I have not done this, but it's also very interesting. We'll talk about dust devils later, and you could theoretically simulate dust devils in a large eddy simulation. I think people have done it for Mars. I've seen some simulations. These ones are more Earth related, but you can use a trajectory model. So it's basically tracing a parcel through the atmosphere to figure out where it came from, or you can use a plume model for volcanoes or more for smokestacks or something like that, and just see where the pollution goes or things like that. But this is the focus of our talk today. So I heard John asking yesterday at dinner, how do you start making a GCM? Or where does it start from? Basically, you need a dynamical core. So this is where all of the GCMs across the world differ. Hardly any of them use the same dynamical core. And it almost always comes from Earth modeling. And this is just computing the fluid dynamics. So it should be, if it's a good dynamical core, fairly planet neutral. It's really, change the constants and things and it should work. But this is what gives us our wins. There's plenty of ways to divide up your grid. This is related to the dynamical core. So the old-fashioned way is latitude, longitude, and it's very nice to read and everything, you understand it. But the problem when you think about it, the grid boxes on the equator are very large compared to the grid boxes at the pole. They get smaller as you reach that polar point. So you have to do some numerical tricks and things to compensate for that. So numerically, it's not great. So most Mars GCM modelers are switching to new discretizations where the grid boxes are more equal all over the globe. So this is something called a cube sphere, and so it makes it harder to share your data with people because they're like, what? You have to put it onto some normal grid. But numerically, it's very good. And there's lots of numerical methods to solve for the equations as well. But that's your starting point. Then the second thing you need is what we call the physics, the physical parameterization. So on an Earth model, you got all these things like moist convection, deep convection, liquid water. Thank goodness Mars doesn't have liquid water. But you have lots of problems and anthropogenic emissions and all that. You pull all that out and you stick in your planet's radiative transfer and all the processes that happen on a smaller scale than your grid box. So we have things like lifting from the surface, mixing up into the atmosphere, turbulence, gravity wave drag. You've even got like how the subsurface and surface heat transfer happens, CO2 and H2O condensation, sublimation off the surface, so your polar caps and things like that. You've got clouds. In some cases, you got photochemistry if you want. So all of this is what makes your planet the planet you're studying. And I've listed the things that are usually included for Mars. One side note, typically happens on a column. So you loop through all the columns and then they talk to each other later through the dynamics, but you're working basically with a whole bunch of 1D models doing these physical parameterizations. Okay, so those are the basic ingredients of a GCM. Just to give you an overview of how many there are. I hope I've got them all, but maybe I might have missed. And some have combined, well, no, they're not combined, but some people from GFDL went to Ames. And so in the US, NASA has models, NCAR has models, Mars Wharf. Another NASA group has a fairly new one. There's MIT Mars GCM. This is kind of upper atmosphere, and then yeah. And then here in Europe and the UK, we've got, of course, LMD, PCM. The model we run here called GemMars, which I'm a bit biased because I'll talk about a lot about it, how we do things, but just because I know how we do things. Max Planck has a model. So Oxford and Open University, they use the LMD physics, but a different dynamical core. So they're not the same model, but they have a lot of similarities. And then the UK Met Office is a new one. Japan, our friend Takeshi runs a very good GCM in Japan as well. Just a couple of fun facts. Most GCMs are written in Fortran, good old Fortran. If you're lucky, they are fully parallelized to run on multiple processors so that you don't have to be too patient. So we divide the lat long grid up into tiles, and then they each run on a processor, and then they communicate back and forth, and it kind of speeds things up. For us, it takes about 24 hours to run one Mars year. It takes a bit longer with chemistry. Chemistry is kind of computationally expensive. And that's at a resolution of dividing the grid up into 4 degrees by 4 degrees in the horizontal, and we use a lot of vertical levels up to 150. We generate a ton of data, and it depends on, of course, how often you output and what you output. Because there's lots of all those physical processes, you can output the vertical diffusion coefficient, you can output the heating rates, things like that. If you output everything you calculate, you're going to generate terabytes. But sometimes it's useful. And if you output at every model time integration step, it's a lot. Okay, so the next part is dust. So we've heard most of this before, so I won't spend too much time, but we know it's the main driver influencing temperature and circulation. We know that it has a seasonal cycle with the dusty season around perihelion. And we know we've seen the interannual variability, which we have occasionally a planet encircling dust storm. And this graphic from NASA Ames just shows all the things that we have to take into account. So we have saltation there, dust devils, we have sedimentation, we have the radiative effects, we have transport from advection, but we also have eddy mixing and possibly convective plumes and all that stuff. So we need to think about all those things. Luca's data here again. This just to show you again, this is time on the x-axis and latitude, so it's a zonal mean, and this is the 12 Mars years, and we've talked about the interannual variability and the patterns we see with this sort of secondary storm. You know, it's not something easily predicted at this stage, but that gives you an idea of dust in the atmosphere. That's opacity, so column optical depth. So it's basically how much dust is in the atmosphere, how thick it appears. How does dust get there? So this was already covered by Gerhard and John. I'm stressing the two main processes: lifting due to surface wind stress, saltation and direct suspension, and lifting by convective vortices or dust devils. There are definitely probably other processes, but the error bars are so big on what we use that I'm not sure we're at the stage right now to include them, but it's still something that we need to think about, I think. But that's how it gets off the surface into the atmosphere. And just a little bit more. Tim, you're getting good use out of this. This is the third time we've seen Tim's picture here. So good work on that. Good. Just showing the idea of saltation, and up here we got dust devils buzzing around. So dust devils occur when you have this sort of, you've got a warm surface, cooler air, you create an updraft and some circulation, and you get dust devils. It's supposed to loop. I go back. Oh, it's not playing at all. Oh, bummer. Okay, so dust devils are kind of like, I don't want to say dominant source, but they're definitely background all the time. Dust devils are happening all the time. And the surface wind stress lifting is kind of what dominates the patterns in the second half of the year. So if you go back to Luca's, this is kind of wind stress lifting regime, and this is kind of dust devils. So it's sort of this background quiet but constant amount of dust being fed into the system. So now we've got it up into the air. How does it get moved around? So if you get it up high enough, it can be advected by the large scale winds. In the sort of the planetary boundary layer just above the surface, you have this small turbulent mixing, eddy diffusion that we have to take into account into a model that gets sort of bumps things up a little bit into the upper part of the boundary layer. And then you have, of course, because the dust is radiatively active, you have these radiative dynamic feedbacks. So you can have the dust heating the air causes an instability and causes it to want to rise more. So this is like, you can have plumes like this. This is modeling result, but it's likely, I mean, no one's actually witnessed it because we don't have someone looking for convective plumes, but we definitely see detached bubbles of dust in the atmosphere in the vertical profiles. You can also have this kind of slow, this is modeling results from the Phoenix modeling scenario based on Phoenix, which landed at 66 North in the spring, summer. And you get this kind of, so if you think about 66 North in the spring, summer, the polar cap is receding. So you get these kind of thermal contrasts, and you get little dust storms happening because you've got this thermal contrast. But instead of causing these like really, because the sun, it's pretty far north, so you don't get this like direct insolation. So you get this more subtle kind of pumping of the these are heating rates, and this is extinction. And so it just causes the dust to go up like slowly, like an escalator. They called this solar escalator. It's a term from Earth, but we were able to simulate it and match the observations from Phoenix. And of course, you can have the dust falling down. So that's the transport and movement of dust. And then we can look at, okay, now we've got the dust up there. How does it affect the atmosphere? So Yannick showed some results yesterday as well. First thing to look at is temperature. This is from Mike Smith, and you see, again, this is time. It's 2 Mars years and latitude. And these are observations of temperature. So you see Mars year 33. This is the dust season. This is the quiet season. This is the dust season. You see a fair amount of dust. Mars year 34, there was the huge dust storm and a secondary storm. And you can see in temperature, this is sort of 0.5 hectopascal temperatures, you can see a reaction to the dust being there, and it causes warming. Okay, so that's good. It also affects things like water vapor, and this is from Shohei Aoki, and he's showing, this is Northern Hemisphere nomad observations, Southern Hemisphere nomad observations. So again, time and height, these are profiles. And you see during dust storms, this is from Mars year 34. So this was the big dust storm, Mars year 34. And then we've got another dust season here, 35. And this is just going into Mars year 36. So this is water vapor in the northern hemisphere, and it's going up quite high. Okay. And also in the southern hemisphere, going up to 80 kilometers. So dust not only impacts temperature, but other trace gases. If you affect water vapor, you have an effect on ozone. So again, NOMAD observed some interesting behavior during the dust storm, the Mars Year 34 dust storm. This is NOMAD observations here, and this is Mars Year 34 Northern Hemisphere, Mars Year 35 Northern Hemisphere, and this is Southern Hemisphere. And this is, you see this dashed line is the start of the Mars Year 34 dust storm, and there was a kind of this layer of ozone, and then just boop, disappeared. And then in Mars Year 35, you have the layer of ozone, but it stays. So we've got this behavior, and it's related to water, of course. But it's a little bit more complicated than that, which is why models are awesome, because we figure it out. So on the other side is GCM simulations. So we also had the disappearance of ozone there. That a cool movie. It's just showing that this is Mars. This is the dust storm year. This is the non-dust storm year. It's kind of a zonal mean sliced onto the atmosphere, and you'll see that the ozone disappears. And what's cool about models is that you can have, in observations, you observe water vapor and you observe ozone, but you can't observe the stuff in between. So models give you that process. You can follow the trail basically. So when you have two endpoints, you've got lots of water vapor in the upper atmosphere. When it gets up there, it photodissociates and you get these Hawks products. This takes away the oxygen, which then reduces the amount of ozone because oxygen is being taken up and is not available to form ozone up there. So it's just kind of a cool use of modeling to connect the dots. We don't have observations of winds, so I just wanted to show how dust affects circulation. So this is actually from model, and I credit Francois. I stole it off of one of his slides. But this is a non-dusty. This is a zonal slice. So you've got southern hemisphere, northern hemisphere, and height. And this is temperature. And this is sort of the meridional circulation. So this overturning cell that you get. And when you have a clear atmosphere, you got lower temperatures and you got like kind of a weak overturning cell motion of air. When you have dusty atmosphere, you get lots of heating and you get a much stronger circulation. So you have to use models to look at the effect on winds, but it's there. Okay, so now we've gone through what we observe in the atmosphere in terms of dust and how we actually put it into the model. So we need a dust lift. We need to get it off the surface. We need to transport it around in a good way, which sounds easier than it is. And then we need to compute the heating rates. Basically, once we get the dust up into the atmosphere, we have to calculate how it affects the temperature. And once it affects the temperature, the dynamics takes care of the circulation. And if you just have those things in it, we can get a dust season that's the same every year. I get a peak at perihelion every year, but it's the same like magnitude kind of. There's no interannual variability, which, is fine. But often we want to use the GCM to compare with observations of a particular year. So that's when Luca's climatology that he presented in the last talk comes in. So we often scale the amount of dust to match the climatology so that we can have a good representation of the temperature and circulation for that specific year. This is just an example of our GCM. If we just lift the dust from the surface, have the model transport it, year after year, I get the same pattern of dust. This is time and latitude, so it's again a zonal mean, and you get this big peak at the perihelion, just one peak. We don't get the double storm or anything like that. And just to compare with 1 year, this is Mars year 35 of the climatology. So, I mean, Quint, they're not that different. You can use this to do your studies, but it's often nicer to have the climatology to study a particular year. I won't spend much time on this, but I put it in for you guys. The lifting due to saltation, we basically use we compute the modeled wind stress. We feed in a roughness length, the temperature and the winds from the model, and we get a surface wind stress. Then we calculate a threshold wind stress to figure out if we should lift or not. And this is based on temperature. And this is actually, we kind of adjust our threshold wind stress based on some of the parabolic flight stuff that was done a few years ago from Gerhard's group. There's a crying emoji because we have a proportionality factor. So this is, again, it's just, it allows us to tune things a little bit. It's a bit of a cheat. But we do take into account gustiness, so you can have sort of more dust lifting in gusty situations. Then we have another mass flux due to dust devils. And again, this is, we couldn't possibly resolve a vortex that's on the order of meters to 100 meters in a 200-kilometer grid box. So we have to figure out how much dust in a 200-kilometer grid box on average might be lifted by dust devils. And this, again, there's, an efficiency parameter and things like that. We do base it on sort of the pressure difference between the top of the boundary layer and the surface. And it provides this sort of background dust coming off the surface. We actually apply these mass fluxes to tracers in 3 size bins, and then we transport them separately, and then we compute the radiative properties after, but we transport them separately. Other models do it differently. You transport the log normal, just the distribution. Yes. We also sediment. I won't go into this too much. Again, I put it in for you guys. We heard about Stokes settling velocity and things like that. Is it okay? Is it right? Good enough? No? Okay, we'll talk again. Okay, thank you. Okay, a note about scaling to climatology. So this is 1 day map. So again, now we have longitude and latitude. So with the Tharsis and Hellas, and it's just the optical depth. So most of us do it. We do it in different ways. You can either just look at how much dust you've lifted, how much your total column amount is, and if it doesn't match, you scale it, and then continue on your way. Or you can compare and say, oh, we don't have enough dust, so we lift some so that it will match. But the downside to this is a column amount, and it doesn't give you any information about how it's distributed in the vertical. Is it all in the lowest 5 kilometers? Is it up to 20? Is it up to 30? Is there a detached layer? We don't know. So we have to rely on the model to give us that information. It is important, though, the vertical distribution, and I'm hoping Antoine will tell us more about the efforts. If you go way back in time, we used to do something called using the Conrath parameter. And it was basically, we would just say, okay, there's going to be this much dust depending on this, the latitude and season. And then we put it in the vertical again based on latitude and season. And this parameter was something that was just set to a number, and it would give you this sort of profile that would just go up. That's the old way. Now, most models are confident enough that they let the dust transport in the vertical and mix in the vertical on their own, but doesn't always match the observations. So we're often adding new processes to try and see what it is that gets the dust in certain vertical distributions. So I'll talk about that later. But I wanted to stress the importance of getting it right and how important it is. So this is from a paper a while ago of the Mars Year 34 dust storm. And this is just a plot of around the dust storm. So when it was the peak part of the dust storm in Mars Year 34 at LS 196. And the black lines are MCS observations. So this is altitude and extinction. So you saw that a lot of dust was seen up to 80 kilometers, quite high. And we tried our regular standard scenario where we just let the model do what it wants to do. And we get a profile that's kind of like this. So this would be the free in the sense that it's free to transport itself in the vertical. And it's not, so we only go up, maybe 60 kilometers. So we don't have enough. We don't get up high enough. The reason we started to play around with the profile was because we thought, okay, Nomad's got these observations of water vapor, and we modeled it, and we're like, oh, our water vapor is only going up to 50 kilometers or something. It's not going up to 80 kilometers like they saw in the observations. And we're like, okay, so the circulation's not strong enough because our dust isn't, something's wrong with our circulation or our vertical transport. It's something the water's not going up high enough. But when you play around with the profile of dust, it does change the circulation. So this is with like not taking into account a dust storm, and these are the meridional mass functions. So you get this sort of 2-cell thing, and it's there. The colors are the water vapor, and it's going up to maybe 60. But if we use the standard Conrath parameter, so that's the purple one. So if you use the standard Conrath parameter, it looks just like our free dust. It's not high enough. But you see that the strength of the circulation as really, it's much, much stronger, and the dust goes up, or the water vapor goes up a bit higher, but not high enough. So then we said, okay, change that Conrath parameter, make it much smaller. And you see the circulation in these, that's this simulation here. And you see the circulation is not that different. So it's not about the water vapor getting pumped up by the circulation. It's actually something else. Because you see in this one, the water vapor is going up much, much higher. So if you look at these bottom plots, this is water ice, and the contours are temperature. And on these ones, it's like the difference between the non-dust and the new simulation. And what happens is, it's not about the circulation, it's about the temperature. And it gets hotter up here when you put dust up a little bit higher. When you put dust up way higher, it gets hotter, and ice doesn't form. So it allows, or the ice forms up higher. So this is really strong ice clouds, and it kind of blocks the water vapor from, it's like a cold trap, it freezes out. But when you make it warmer, the water vapor is allowed to go up to the higher altitudes. So it's much more complicated than just pumping circulation. It's about, you have to have the water ice clouds in there to affect the temperature, and not have water ice clouds to get it up high enough. So it is crucial to do it right. And related to that is once you get the dust up into the atmosphere, then you have to compute the heating rates. So this is where Olga and Yulia come in. Most, I don't want to say most. There's different ways to do the radiative transfer. This is the way we do it. It's actually exactly the same way as LMD does it. We have 5 wavelength bins. This is wavelength and extinction, single scattering albedo, and asymmetry factor. The black line is from Mike Wolf, and the blue lines are, so you have to take an average for the bin and use these to get the inputs to the two-stream radiative transfer. And what we get out is heating rates. So there's plenty of room for improvement here. I don't know if using more wavelength bins is better, probably, but this is what we use right now. So when you put it all together, I'll just go quickly through this. This is a comparison of MCS, so it's seasonal zonal cuts. So this is MCS, this is GEM, this is temperature here, and dust extinction. And this is for LS0. It's just for a 5 LS chunk. So we don't do too badly compared to MCS. And actually our vertical, this is from Mars year 35, by the way. And even our dust, so it's not bad. It is scaled to Mars year 35, but of course the vertical profile is determined by GEM. This is LS90, so now you got the northern summer. Again, not too bad. This is LS180. Again, I don't know, looks pretty good to me. And this is the the southern summer. So you have hot temperatures here and very cold pole, and we're not quite cold enough there. But not bad again. We get general shape right and things. So that's when you put all those things together, and just to show you that the model works for the most part. Okay, now we come to the problems or the open questions. Interannual variability, nobody's got that right yet. One of the interesting things I think to talk about is size distribution of particles of dust in the atmosphere. Again, talking about the radiative properties, are we getting them right? What kind of shapes are they? The lifting from the surface, are we doing, is it good enough what we do? Or should we be putting in more advanced information? And the problem of the vertical profile. So when I showed those zonal average, 5, you don't see these specific events where you have these detached dust layers and things. And those are important, and we don't get them. Most models don't get them right. So just a moment about interannual variability. No, we cannot predict the next dust storm. Some people will tell you they can, but no. So this is a plot from a model simulation of 30 years by Mulholland in 2012. And what he did was he kept track of the dust on the surface and used a varying threshold based on the amount of dust available. But great. But if they just let it go without thinking it'll all be fine, it all just goes away, and you basically lose the dust cycle. So they have to inject dust in places, and it's a bit, there's a lot of this. And the knobs that they turn are set to have a big dust storm every 3 years. Now, if you remember from Luca's climatology, okay, the first 2 were 3 years apart, but then there was a big gap, and it's not 3 years necessarily every. So if you have to tune it to say there's going to be a dust storm every 3 years, then to me that's not predicting. There's another theory of the orbit spin coupling. I don't know if anybody has a better feeling for this. I don't know. It's about the the solar radiance and the angular momentum timing, they seem to think that they can predict the next dust storm, but I don't think they can. So this idea of the finite, so I didn't mention actually that when we lift dust from the surface, we assume there's always dust available to be lifted. But in reality, that's probably not true. So we are attempting to implement this idea of a threshold based, like change the threshold based on the amount. So the first step is just to keep track of the dust that lands on the surface. And this is, oops, sorry, this is just a snapshot of our work so far. This is from this again. This is all roadmap work. So Gerhard and John gave me one equation to rule them all for the lifting of dust. It was a great summary of the things that can affect the shear stress. So gravity, cohesion, thermal creep, delta P, and charge. So they talked all about that. I played around. I just did some back of the envelope calculations, and I just sort of, this is threshold wind stress, and I played around with particle sizes as well. They gave broad ranges of values to plug into these different parts of the equation. This red line is sort of the kind of back of the envelope GEM-Mars threshold for lifting. And depending on particle size, it can be a high threshold. Sometimes we go below that. These are, I think this and over here are my three size bins. All in all, it was difficult to do in a short period of time in this project to really investigate thoroughly. But often it wasn't, the threshold was too high and I wasn't getting enough lifted. So it's future work to think more about that. One of the other parts of the project is microphysics. And to start with microphysics, we're doing more bins. So we do size resolved dust and water ice. And we went from the 3 bins to 10 bins, and now we're using 20 bins. And this is just for dust. So this is dust extinction profile for just I think it's LS 180. And when we put more bins, this is 10 bins, this is 3 bins. When we put more bins in, we get extinction higher in the atmosphere. So this is an interesting idea. It's very new. We're still working on it. But it could be, so we don't do a log, we don't do a bimodal. It is really those bins transported individually. Yes. Just to be sure, because yeah, it's not. It's yes, and it's 180. Yes, sorry, that was just it really is. This is a snapshot of the dust particle radius. So again, latitude, this is for a different LS. It's right at the beginning of a model run, but you can see lots of interesting detail anyway. So like I say, this is very preliminary, but I think it can lead to some very interesting results on both the horizontal and vertical distribution of dust. Yes. Yes. Well, this is, yes. So I think this is 10 bins still. Yeah. Yes, mean radius for the bins. Also part of roadmap, we took the radiative properties that Yulia so kindly presented to us. So they were working just in a smaller visible wavelength range. So we could only replace these 2 bins, and she gave me the extinction efficiency, single scattering albedo, and asymmetry. And that's these other lines. So the one big difference is the single scattering albedo. It's much higher. So I plugged them in, and as we expected, this is for MCS, LS 300 daytime temperature difference, because I figured it's visible. I'll just do the temperature difference. So this is the temperature difference of our original optical properties with MCS, and this is with the new optical properties. So it's much colder, and this is the difference between the two optical properties. So the old properties of Mike Wolf are much warmer, as you would expect. So we're capable of changing them, but I don't know what to do, because it doesn't make it better. It does in some places, like, because you could argue it's better. No, it's not better. No, it's different. So that's something we can continue to work on. And this is about the vertical distribution. I took this again. I stole this from one of the LMD group with the paper about the rocket dust storms, Chao Wang, and okay. So this is MCS observed dust density scaled opacity, and so this is sort of in time, and this is a latitude height plot. So you see this like blob, and without rocket dust storms, you don't get the blob. With rocket dust storms, you get a blob. So that's a good result. From what I understand, it works a lot. But don't you get rocket dust storms more often than you wish? Is this true? Okay. 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 Yes, if the scenario is wrong, we're all wrong. Okay. So basically, I will leave this for Antoine to say more about, maybe, because I know you did some work on upslope winds, and I didn't add this in, but I'm also looking at our vertical diffusion, because we tend to our like the eddy mixing, we tend to have a really good boundary layer, but it drops off just a little early, and it's the way we define stability in our vertical diffusion, and that's something that could help us also with the mixing in the vertical, but that's another thing. So there's lots still to do. Ooh, I'm getting there. Just a note about public access to GCM data. If you don't know about the Mars Climate Database, you should. It's very easy to use and very, very useful. There is also an open GCM. It's basically data assimilation from the UK, Open Mars. It's available online. There's an American one that also uses data assimilation, ensemble data assimilation. There is Vespa that Loic talked about, and GemMars is available there, and TGO Nomad Observations also. It's hard to use, but have some patience. You can get stuff out of it. And of course, the best thing to do is just to ask the modeler, because they can provide you with a custom simulation, exactly what you want, when you want, where you want. And that's one of the best things to do, because most of us are quite happy to provide. We want people to look at our data, because we look at things often in one way and then we miss things. And when someone gets into the nitty-gritty details, they see other things. So it's good. Just a couple other useful references. The Atmosphere and Climate of Mars is a good overview if you're looking for information about both modeling and just the basic atmosphere. This is it's Earth-based, but it has all the fundamental equations of modeling. Past memo abstracts are a great resource as well. And the last model intercomparison, if you're interested in model intercomparisons, we did all participate in an intercomparison for Jezero Rotator. It's very specific, but it's still an interesting sort of overview. I think I'm almost done. Oh, I put that in because no. And so I often get asked, we were just talking at lunch, so I threw this in. This is MCD and GEM, MCD GEM, and this is for LS90 and LS270. So the two solstice seasons. The top is temperature, the middle is dust. It's for two different, this is Mars year 33, this is Mars year 35, because you don't have Mars year 35 in the climate database yet. 6.1, it is 6.1, yeah. Okay, I did not see it. And this is ice, water ice, extinct, no, VMR, water ice VMR, dust VMR. Anyway, they're two different years, but they're low dust years. So it's, so I'd say we do all right. I'd say we're, sometimes simple is when you don't include all the details, you still get it right. Okay, that's all. Yes, Luke.
Great talk. I mean, it's a great summary of modeling effort, at least from one model point of view. So two things. One, I repeat what I said before. There will be a Oxford University data simulation multi-year available
great.
soon.
Good.
To cover all the years that haven't been covered by Magda 1. So it'll be Magda 2. So you can.
But I think Open Mars is also newer than Magda.
Open Mars is newer than Magda 1, yes, but Magda 2 will be newer than in terms of
and that's
coverage.
Oxford.
And that's Oxford.
Okay.
That's
You're right. I should have put Magda.
No, but I mean it's not there yet. I mean it's not. It's
no, but
not
I should have put the first Magda on.
But the question I have is more related to the relative impact of dust devils and local storms in determining the background dust in the boring season when no large-scale dust storms are occurring. Because if you look at, well, we know from images, and we also see these signatures in the climatology, we know that we have local storms around the cap edges, both northern hemisphere, southern hemisphere, in northern summer. So where is all this dust going? I mean, the models might not resolve specifically these local storms because they are small scales. But could these storms account for the background opacity rather than these dust devils, which to me always look a bit too weak to have enough? I mean, you can tune, of course, in the model, you can tune the parameters to fit. But then do we tune the right physical process?
I think when I said that the first half of the year was dominated by dust devils, it doesn't mean it was all dust devils. We definitely still get some wind stress lifting, even resolved by the model, certainly by the cap edges. We get dust lifted by our saltation parameterization. So that is there. Maybe I overemphasized the dominated by dust devils, but you're absolutely right that we don't resolve, or maybe it's a dust reservoir issue. Maybe lots of dust gets settled there and therefore more gets lifted, or we don't know. We're honestly.
Because, I have also the same kind of problem with this theory by, I don't know if I should call it theory or hypothesis or whatever, by Shirley et al. Related to this spin orbit coupling, right? Because they showed with a GCM that it works magically.
Magically, this is. I agree.
But the thing, I think there is something interesting there, because what they use, if I remember correctly, they tune a specific parameter to implement this effect into the GCM, right? And if this parameter has a value high enough, they get indeed a prediction, good prediction, good statistical prediction. And if this parameter is low enough, they don't get it. It doesn't have any effect. So what I wonder is, are we maybe missing? I mean, we can tune anything, right?
Sure.
You can write an equation, you tune it, and you fit it, and it works. So
we don't like to do that.
No, we don't like to do, because we want to base on physics.
Yeah, definitely.
But maybe, are we maybe missing something which, if it is tuned enough, then we get it right?
Who knows?
I mean,
it could be a compilation of available dust on the surface and solar radiance and angular momentum. Who knows? But whether that's the thing, I don't think so.
So I mean, do they? Let's put it this way: did they find the right term to put in the model that, tuned in the right way, produces the good results, but for the wrong physical reasons?
Yeah.
Or
we often can have two wrongs make a right, for sure. That can happen for sure. I don't know enough about it.
Yeah, on that point specifically, I don't know anyone who has managed to work through all the equations from Shirley and get to the same results.
Yes, yeah.
I think the reviewer did not. Well, the reviewer didn't do all the equations clearly, and that's probably the explanation. And so that's why many people say, yeah, but no.
Yeah, but no.
That's one thing.
Yes.
But to kind of continue on this tuning topic, for instance, I'm still trying to reconcile what you show with the new dust properties, with the scattering LBO changing. So I think you're a bit harsh in your conclusion. Well, that's a conclusion when you say, okay, I changed the dust optical property. Now my model is worse than before. But we should never forget that we always tune everything. So in principle, you should, once you make a big change, and big is relative term, in the model, you probably should retune it. So for instance, you have this tuning factor in the lifting of the dust. So if in terms of radiative transfer, you're thinking...
That's a fair point. It's a fair point.
I should lift less dust.
It's a fair point.
I changed it's now, no, it's the other way around. Sorry. You should lift more dust because its albedo is now higher so that you get the same net radiative heating. That could work.
It could be. There's so many factors that could change it. You're right. I'm sorry for being harsh.
No.
No, you're absolutely right. You're absolutely right.
And I was also thinking, so about these three, how many bins is enough to represent? So three bins actually works fine so far for you. And I was wondering, did you ever check, when you have these three bins, how much each population contributes to the whole opacity?
Not in a way that is rigorous, but I think that will be in the next.
Because when you have these three populations, when you inject them, do you inject them evenly, or because of course the big particles will fall back down rapidly?
Yes, yeah, exactly. So the flux is applied to the three, and then
they're all equally.
Yeah, the flux is applied to the three based on them.
Small ones will stay up there much.
Yeah.
Again, the tunable lifting parameters, the dust level and near surface wind parameters, are they grid independent or grid dependent? Have you already checked, like running the same simulations with 5, 2, and 1 degree?
How much time do you think I have on my hands? No, I don't change my resolution that often.
Okay, so
no, I haven't.
because there is a paper
Sure.
about the differences of these lifting parameters between 5 and 2 degree.
I'm sure you would have to tweak things for sure. But honestly, I don't change my resolution that often. It's a special day when we run 1 degree, let me tell you. Yes, Christmas. No, not Christmas. But summer holiday when no one's around and we can use the computer to ourselves. No.
For this Conrad profile for vertical dust distribution, do you guide the model also with the Mars dust climatology, or it's just?
Yeah, we can do either one. We can either just let the model do its thing, or we can correct. But we only have one value, the total optical depth. So the model, the vertical profile comes from the GCM. We don't input a vertical profile based on observation. I just did that for that one experiment just to see what was going on with the water. That was just a special test.
If you don't change your spatial resolution, did you try to see the effect on the dust lifting of the temporal resolution, like changing your physical time step and see if it has an effect on the dust lifting?
I have changed my time step, but I did not find it made a difference. Would it make a difference?
Not supposed to. But...
I can't. I'm just looking at what goes into it. I don't think it would, really. Because your temperature's being updated. You're just, like, it's really based on the conditions right at that very moment, whether it's 15 minutes or, yeah.